So I welcome you students. We will see what resonance is once again, the conditions. We agreed upon that resonance is a situation wherein we can draw more than two resonance forms or canonical forms for some molecules by placing electrons differently. But these molecules must be conjugated systems like this. It should have a double bond, single bond, double bond, single bond, double bond. And the conjugation we have seen details. If it is like this, there is no conjugation, it can't show resonance stabilization. You can also satisfy yourself by looking at this example. This molecule called as hex 3 in 2 has a resonance because it has double bond, single bond, double bond system. Whereas its isomer hex 5 in 2, although it has same formula, it doesn't have the conjugation, so it is not that stable. It has a stability and lower heat of hydrogenation. It is less stable, so its heat of hydrogenation is relatively little more. Now we will see what are the conditions for resonance to occur. First of all, the hybridized state of second period elements must be either sp or sp2 and they should be in conjugation. Okay. Now while writing the resonance canonical forms, you can't change the relative position of atoms. For example, you are trying to write a canonical form like this. Now you know how to move the electrons. You move the electrons like this, you move the electrons like this, and you shifted this H plus to oxygen. This compound is called acetone, and by doing this operation you got something called its enol form. Here you have changed the relative position of atoms. The hydrogen which is bonded to carbon has been shifted by you to oxygen. This is not legal. This keto-enol tautomerism will never come under the heading of resonance. They are not canonical forms because you have shifted the atoms. So while writing the canonical forms, relative position of atoms should not be changed. Total number of electrons and the total number of unpaired electrons should remain same in all the canonical forms. Notice that you can't tamper with the number of electrons. You see, this is called allyl carbocation, and you can't say this is its canonical form by writing allyl carbanion because they are differing in the number of electrons. Canonical forms will never differ in the number of electrons, which is wrong. Next point is, while writing canonical forms, you notice that the greater is the number of pi bonds present in a molecule with no charges, greater is its stability. For example, for benzene, you can write C6H6, double bond, single bond, double bond, single bond, double bond. This form is more stable and because it has no charge separation. And of course, it is equally stable. The position of double bonds is being changed. These two canonical forms contribute a lot. They are called forms. Whereas you can write another form like this by shifting the electrons here and like this. But this particular canonical form, although you can write possibly, contributes very less because it involves charge separation. So canonical forms which involve charge separation contribute less. Equal canonical forms contribute more. So the forms without charges contribute more than the forms where there is charge separation. Notice that the forms where octet rule is obeyed, where all the second period elements have 8 valence electrons, contribute more, they are more stable than those where the octet rule is not obeyed by all the atoms. Also, in all canonical forms, for any second period element, maximum 4 electron pairs are allowed in the valence shell. The 4 electron pairs can be bonding pairs or lone pairs. Put together, total number of electron pairs can be only 4. You can't write 5 electron pairs around nitrogen, which is wrong. Let us quickly review it in real situation. This is called acetyl carbocation. For acetyl carbocation, the C can have plus charge, or else this oxygen can contribute one of its lone pair to make a triple bond. It is another canonical form. Of these two canonical forms, this is more stable, more contributing because every atom has octet. Though there is a positive charge on oxygen, every atom has octet that contributes more. Here the carbon has only 6 electrons, it does not have octet, so it contributes less. You will be really surprising, but it is a fact. So, oxygen won't mind to have positive charge formally. Now we are looking at next idea. Generally, if you have canonical forms where negative charge is resting on more polarizable atom contributes more. Polarizability is a property which you can observe down a group. Selenium is more polarizable than sulfur than oxygen. If we have thioester acid, for thioester acid you can write to canonical form when once it forms a thioacetate anion. Thioacetate anion is formed when thioester acid loses a H+. This is thioacetate anion. This thioacetate anion can have negative charge on sulfur and the negative charge on oxygen. Out of these two canonical forms, this canonical form where negative charge is resting on sulfur contributes more. This is very stable. This is a very important point. So first important point is negative charge should rest on atom which is more polarizable. Now if you don't have more polarizable atoms, if you have more electronegative atoms, then the negative charge should reside on more electronegative atom to the extent possible. You can see here, this is a carbon ion, negative charge is there on the carbon. Its canonical form, negative charge can become a double bond and oxygen can take negative charge. This canonical form contributes more because here more electronegative oxygen is having negative charge. So if you have only more electronegative, less electronegative atom, negative charge better should remain on more electronegative atom. If you have more polarizable atom, of course negative charge prefers on more polarizable atom. Okay. Next, more electronegative atom gets negative charge, that gives more stability if there is only one more electronegative atom and the other one is less electronegative. Notice that canonical forms where similar charges are close, they have negligible contribution. You can't have two plus plus charges, two minus minus charges close by. Canonical form where there is opposite charges, the canonical form where there is opposite charges, it is better the opposite charges should be as close as possible. That's an idea. You can see here, the phenol, if this is a situation, the lone pair is becoming a double bond, the double bond is going to. Notice that phenol has this canonical form. This form is more stable because it has no charge separation. This form is less stable because it involves charge separation, right? So these are some rules to write the canonical forms. Can you see out of these two which is more stable? Obviously this is more stable, this is less stable. For this carbocation, out of these two which is stable, this is more stable because here every atom has octet. For this which is more stable, this is the only possible existing form. This is impossible because in this the nitrogen is getting 5 electron pairs, which is impossible. You understand? Therefore, first and most important priority you should give for which has no charge, more pi bonds. Second importance is for which whether every form has octet. Third thing is whether it is violating the rules of valency. Normally they will give you canonical forms and ask you which is more contributing and more stable. You should be vigilant. That is a very commonly asked question. Now before we close this discussion, quickly we see what are the effects of resonance. Resonance can bring about variation in bond lengths. For example, in benzene, due to resonance, CC bond length is found to be 140 picometers, which is longer than the C double bond C bond distance and shorter than C single bond C bond distance. So resonance can always bring about variation in bond lengths. Resonance can bring about extraordinary stabilization to a molecule, which is manifest in the lowering of heat of hydrogenation, heat of combustion. And resonance can account for extraordinary acidic behavior and extraordinary basic behavior of some molecules. For example, guanidine can show extraordinary basic ability because the guanidinium ion is resonance stabilized. Very quickly we can see this is called guanidine. When it captures a H plus behaving like a base, it gives guanidinium ion. This guanidinium ion has three equivalent resonance canonical forms. The double bond can be here, the double bond can come here, the double bond can go there also, right? So you can write three canonical forms for guanidinium ion. This extraordinary stability of guanidinium ion makes guanidine a very powerful base whose pK is 13.6. pK is 13.6 means very strongly basic, right? So the resonance can bring about variation in bond lengths. It can give extraordinary stability to molecules where it is possible. It can account for the acidic basic strengths, and it can also explain why the unexpected products are formed in some reactions. All these further details we see in the next video. Thank you.